Hello, everyone. Welcome back to your series of probability and statistics. We will be done with the tests of hypotheses and confidence intervals today by looking at the difference between two population proportions. So, in this case, we want to check to see whether two populations have the same percentage of a particular parameter or not. Okay, so how do we do that? Notice that the confidence interval and the hypothesis testing are two faces of the same coin, like we said. But we mentioned earlier that if we had large samples from populations and we calculate the proportion p of each, then we can approximate that if p or if the number of successes in each population is more than 10, or some people say even more than 20, then the approximation would be very good by the normal distribution. So we use the normal to approximate the binomial, which basically is the basis for proportions. So we are going to assume we have two populations. So here is population one, and here is population two, and some quantity here is x1 and some quantity x2 that so I'm going to select a sample of size n1 and n2 from here and found that x1 of these uh, like are um, inside the event I want to estimate, and x2 is the same for population 2. So I'm going to say, okay, I'm going to check to see if this proportion x1 over n1 is the same, or the ratio in the population from which I pick the sample n1. I found that I can estimate the proportion of all the x's here as x1 over n1, and the proportion in this population is x2 over n2. Usually, I'm going to say the null hypothesis. In the null hypothesis, I'm going to say P1 equals P2. I don't like to write it like that. I always prefer to write the parameter on one side and the constant on the other. And I always prefer to use pi1 and pi2, not p1 and p2. But anyways, so we're going to say p1 minus p2 equals 0. The alternative may be not equal to 0 or less than 0 or greater than 0, depending on the case. It doesn't matter. But remember that whether we are finding the confidence interval or we test of a hypothesis for the mean or the proportion, let's write it for the mean. So if I'm estimating mu for one population, I used to say x bar minus the estimator of x bar over the standard error of x bar. So we always do that if it's a mean or a proportion. And we said the expected value of x bar was mu, you know that. And if I know I never do, but if I assume I know the population variance, that would be over sigma over root n, which can be written as over the square root of sigma square over n. It's the same thing, right? Or I replace that by s. And with the proportion, we do the same thing. We say, okay, I'm going uh, to estimate that. So I'm going to call maybe the estimate x1 over n1 is p sub a, and the estimator of p2 is p sub b, because I'm taking samples, right? This is whole population, but I'm taking a sample. And I want to subtract from that p1 minus p2, which is 0, so I will ignore that later. But I have to subtract the estimator of x bar, or the estimator of P1 minus P2. And then I divide by the standard error, which is sigma over root n, but I have two n's. So how can I calculate the sigma? Here comes, you know, arithmetic for help. Suppose I have two proportions and I say One half equals 5/10. Yeah, it's correct. Correct. But now, if I assume they are equal, because notice we always assume the null hypothesis is true, and then we see if we have evidence to reject that. So if it's true, but the sample sizes are not the same, and I don't know what to use here. I say, oh, I know from arithmetic that if I have two ratios or two fractions that are equal, I can combine them together and say 1 plus 5 is 6, 2 plus 12 is 2 plus 10 is 12, and 1 half is the same as 6, 12 is the same as 5/10. So that's exactly what I'm going to use here. I'm going to say, oh, let me get an average proportion which equals x1 plus x2 over n1 plus n2. And I'm going to call that p bar. 1 minus that would be called q bar. So I'm going to divide by the square root of p bar q bar over n1 plus p bar q bar over n2, which can be eventually become PA minus PB. Notice this is 0 from the null hypothesis because we always check whether they are equal or not equal, or equal and one is greater, or equal and one is not greater. So P1 minus P2, I'm not going to tell you, do you think the difference in proportions is 0.05 between the two or zero point 0.2? Why? I want just to see if one is better than the other, right? Not better by what proportion. It doesn't make sense. So invariably, this will be 0 in your problems. Some people prefer to factor out the PQ, so they say P bar Q bar times 1 over N1 plus 1 over N2. You can use either, it's the same. So let's take an example. And of course, if you want to construct a confidence interval for P1 minus P2, and it's a two-sided, then you say it's greater than PA minus PB minus Z alpha over 2 times, times the square root of P bar Q bar over N1 plus P bar Q bar over N2 less than PA minus PB plus Z alpha over 2 times the square root of P bar Q bar times 1 over N1 plus 1 over N2 is easier. It's the same thing as we said. If it's a one-sided upper or lower bound, then one of them would be just this minus this alpha, not alpha over 2, or this is greater than this minus that alpha, also not alpha over 2. So let's take an example and see how easy it really is. Of course, you can use a calculator to solve, and we will use the calculator to check our answer later. In this problem, they tell you, policemen wanted to check to see the proportion of people wearing seat belts, and that was like over roughly 25 years ago in New York City versus Boston. So they took a sample, random sample, they, collected data. In New York City, they checked 220 vehicles, and in Boston, they checked only 117. And they found in New York City, 183 people wearing their seat belts, while in Boston they were only 68. But of course, the number is not the same, so the ratio, we can calculate the ratio of each one. That's what we need to do. But we are going to to say that the null hypothesis is again P1, which I prefer to write pi 1, P sub 1, which is New York City, minus P sub 2, which is Boston, equals 0, versus the alternative hypothesis that says, is there a compelling evidence that the people in Boston, the proportion of people who are wearing their seat belts in Boston is significantly less than those in New York? So I want to see if P2 is less than P1, or P2 minus P1 is less than zero. But since we wrote P1 first, it's it's the same as saying, is there compelling evidence that people in New York City who are wearing seat belts are way more than those? So I can say P1 minus P2 is greater than zero. That's what I want to check. Or I could have said P2 minus P1 is less than zero, but since I started by writing P1 minus P2, I would write this P1 minus P2. It makes more sense. And let's check at alpha equals 0.05. So what do I need to do? I want P sub A, which is the proportion of people in New York City wearing seat belts, and P sub B for Boston. So for New York City is 0.915. No, I divide by 200, not 220. I'm sorry. 183 over 220 is 0.832, roughly. And that in Boston is 68 over 117. It's 0.581. It looks big, right? But we are going to see. Notice that we are having only a one-sided test. So I have to reject only for, I would compare with Z alpha. And Z alpha at 0.05 is 1645, right? Yeah. So I'm not going to say alpha over 2 and alpha over 2. If they said, is there evidence that the proportions are equal or not equal, then in that case, I would have Z alpha over 2 on the top and Z alpha over 2 at the bottom, or negative Z alpha over 2. Okay, so let's first calculate P bar, because P bar is the average proportion, 183 plus 68 over 220 plus 117. So let's do that and see what proportion do we get for the standard error calculation. 183 plus 68 divided by 220 plus 117. 0.745. So Q bar would be 1 minus that. 1 minus that. It's 0.255. Okay. Now let's calculate Z calc. Z calc is, notice we are starting with P1. So we say 0.745 minus 0.832 minus 0.581 divided by the square root of 0.745 times 0.255 times 1 over 220 plus 1 over 170. And see if that's greater than 1645. So we say, yes, there is a compelling evidence that those in Boston wearing seat belts, the proportion of them is less than New York City. If it's less than 1645, then we reject, or we fail to reject, and we say, no, we don't see compelling evidence for that. You should be familiar now with the language we use in probability. 0.831 minus the 0.58119, that's the numerator. And then we are going to divide by P bar, which is this, times Q bar, times 1 over 220 plus 1 over 117. Hopefully we entered it correctly. Wow, you got 5? That seems too high. I'm not sure if that's correct. So we will reject, but 5 is so large unless I did something. Well, let's do it with the calculator, and then if we get the different value, I will come back and check my work because doesn't look right. Stat, if I go to test, you see here we have two proportion Z test. That's what you can click 6 or you can go to it and enter. So it asks me what is X1? X1 was 183. I can enter this as X1 and this is X2 and say it's less than, which should be better because they ask you if this is less than that. So let's do that. It doesn't matter really, we'll get the same answer. But if I enter 68 out of 117, and this is 183 out of 220, and I want P1, P2 is less than P1. So I have to select less than now because I entered Boston first. And then I say calculate or draw. You can do both. Draw will give you both. Yeah, it's negative 5.024. Wow, that was a very weird problem because we know this is way greater than 1645. So we will reject the null hypothesis, which means we accept the alternative that the percentage of people in New York is wearing seat belts is much higher. Or, as I said, if we do it using what we did in the calculator, we say the percentage of people in Boston wearing seat belts is much less than that of New York City at 5% confidence or at 95% confidence at alpha equals 0.05. Even if I make it 0.01, it would be around 2 or something. So it's like 5.02 is way higher. And we could see that from the numbers, right? So it was really very simple to, even we didn't need a test for that. Let's take another problem. And this problem was about efficiency of a drug. And this drug was to prevent colds, okay? And given that it was given to males and females. So they tell you male, female, number, and then the people who got cold. So X is how many got cold after taking the medication. So for males, they checked 200 males and only 100 females. Okay? And they found that 38 females got cold after taking the medication. But in male, they were, I think, 102. That's what my recollection. Okay. Since we did the last one, well, we can do both greater than or less than, but we did one of them. So maybe I say it looks like female are less likely to get cold, so it's more effective for female. So we can check that as the alternative hypothesis, or we can say, oh, do you see a difference between them? It's both of them are fine. So, and maybe we can make it just to be more careful. Let's put alpha equals 0.01, so make it harder to prove. And let's say we want to see if females are less than male. Okay? So our null hypothesis is that P1 or the actual proportion of males who uh, are getting cold, we want to check if this is higher than that of female. That means it's better for female than male. So here higher means worse, right? Because these are the people who get cold, who caught cold after taking the medication. So if it's a large number, it says the medication is not that effective. And if it's a smaller number or a smaller proportion, that's better. So be careful with the wording. So here we say P1, if you call that 1 and 2, minus P2. Now they say you are sexist. Why did you say male is 1 and female is 2? Maybe the higher number is better. Who told you? Okay. Equals 0. And the alternative hypothesis is that P1 minus P2 is greater than 0, right? The number catching cold or the proportion catching cold in male is higher than that of female. So that's worse, right? And alpha is 0.01. So we need to calculate three things. Lowercase p1, like we can use p hat, it's better. Last time we said pa and pb, but it's really p hat. It's the estimator of p1, which is 102 over 200 or 51%. And p2 hat is 38 over 100. That's 0.38%. So I don't need a calculator for those one. And then we calculate P bar, which is 102 plus 38. That's 140 over 300. So what is that? 14 is 0.4666, 4667, right? Yeah, it should be. And Q bar is 1 minus that, so it's 0.5333. Of course, these are, it's 666. So since I used this, to be to be correct, mathematicians would kill us if we say 4667 and then we use, so it should be 0.46 with a small zero on top, right? Okay, so now let's calculate the Z calc. And here I will have to check what is Z 0.01. It's like 2.33 or something. We'll see. So 0.51 minus 0.38 minus 0 over the square root of 0.466 times 0.533 times 1 over 200 plus 1 over 100. And use the calculator and get, let's clear those. So I know the numerator is 0.13. There is no reason to do that. Divided by the square. Oh, no, we didn't. So let me do it correctly. 140 over 300 and 1 minus that. And then we can say 0.13, the numerator, divided by the square root of this guy times that guy times, yeah, we don't have to say times, 1 over 100 plus 1 over 200. Oops. Right? 2.13. If you do it female minus male, it would be negative, like we learned that. Okay, so now we can go to the test again, stat, tests, and then enter 6. We can say x1 is 102 over 200, 60, oh, I'm sorry, 38, not 68, that would be horrible, over 100, and we want it to be greater than P2, right? P1 is greater than P2, meaning the males catching cold is higher than the proportion of female catching cold. And let's draw it again like we did last time. 2.127, correct? And the probability is 0.0167. So at alpha equals 0.01, you really, what? What do you do? P-value is higher than alpha, so you fail to reject, but you say, oh my God, that's close. The difference is 0.00666. So probably if I take 0.05 here, definitely I would reject, right? Because it's much less than 0.05. But if I want to be sure, with high confidence that I'm making the correct decision, I decrease alpha. Notice, but by decreasing alpha, you are increasing beta. We didn't discuss beta in this course, but it's, you know, we can go back to that later, or maybe in a more advanced class. So we say we fail to reject at 1%. But if we're not that critical, if you will say, okay, at 5%, oh, definitely, it's better for female. So here you see where the confusion comes from in statistics. Is where do you set alpha and beta? How how critical it is. So if you want to be really very confident that you are not rejecting a, um, a true hypothesis, then you care about alpha, right? But again, keep in mind that if you are rejecting this, you may be accepting the false hypothesis that they are not true, but their beta is very high. I don't know if it makes sense to you, but once we cover alpha and beta in more detail, you will see why that makes sense. As I told you, this is like a balance. If you increase one, the other one decreases. The only way to decrease them both is to increase the sample size. But maybe you couldn't get more than 300 people in this experiment, or it would be too much, too expensive, right? So if you set it like that, then you have to carefully select alpha. And in real life, you would say, okay, so what difference in proportions is really significant for me? And if you know that, you can set it to calculate beta. And using those, you can adjust alpha and beta for that level, or you say, no, these are still too high. Then in that case, you have to increase the sample size. So it's a little tricky, but the software can help you with that. In fact, our studio can do it for you. But for now, I think it's clear. It's so easy because we assume that the proportions are the same. So p hat or p bar is easily calculated. You just add the x's over the n, and the rest is history, as they say, right? Okay, so if that doesn't make sense to you, or if you have any questions, please let me know by sending me a comment, and I will get back to you as soon as I can. Thank you very much for watching. Hope to see you soon.